yesterday's class, we were looking at Cascode current mirrors, and we were trying to look at it from, we were looking at it, and we saw that it has two major advantages. And if you recall what we saw in yesterday's class, we said that, it solves two problems. One problem is basically the problem of, the systematic mismatch. And the other problem is basically the problem of output impedance, right? So yesterday we saw how this Cascode thing solves the problem of systematic mismatch. So when we say systematic mismatch, we are talking about the mismatch between the VDS of both the transistors. So if you have M1 and M2 being the mirror transistors, we see that the VDS of M1 and the VDS of M2 needs to be equal, and therefore this one solves the problem of making sure that both the VDSs are the same. So this is M1, this is M2, and you're putting another M3 here, biased it in such a way such that VB is equal to VGS3 plus the VDS of 1, which turns out to be VGS1. Okay, so systematic offset problem is solved, and we started off with the calculation of output impedance. Right now, in order to calculate output impedance, we said we will draw the small signal model, and I also gave the justification why we have to go for the small signal model, because what happens is if you take this node Y, let's call this node X, right? There can be some kind of a small signal variation happening at this node Y, right? So under normal circumstances, what happens is you can kind of picture it as being, a current source like this with a certain R out, right? And here you are having some voltage which is going to vary like this. So obviously what happens is the current, let's say the current that is flowing here, let's call it as the I out, let this be the I naught. Now this I out is also going to depend on the voltage variations that you're having at this node Y, right? And so how much that current will vary depends on the R out that you have. So lower the R out, you'll have more variation in current depending on the small signal voltage at this node Y. All right. So what we are interested is basically to capture or to calculate what is the small signal output impedance, right? And in order to do that, we had drawn the small signal equivalent circuit. So since this is the first small signal analysis we are doing for this course, I'll just go a little slow to make sure that all of you are on the same page, right? Now we are going to look at only this particular section. This is our M3, this is our M2. Let's call this node X, let's call this node as Y. And in order to find out the output impedance, basically what we do is we connect it to a test voltage source, right? And we want to measure what is the test current that is flowing, and that will give us what is the output impedance, right? Now, what is the voltage here? The voltage here is a VGS1, which is equal to VGS2, which is a DC voltage. There is no small signal component here. Okay, so let me just add a note here. There is only DC, no small signal AC. All right. What happens here is that here again, the voltage is VB. Now this again is basically a DC voltage. It is DC only. All right. Okay, so let us go and build our small signal model. So we had already done that. So this gate 1, let's say this is gate of transistor 2 here. I am grounding it, right? This is source 2, which is also grounded. Right? In small signal model, what do? We set all for, let me just put for small signal analysis. What we do is set all DC sources to 0. Right? So in other words, here the DC voltage is set to 0. There is no AC, right? This is at ground. This is at ground. So VGS2 is basically equal to 0. Right? And so what is this? GM2 times VGS2, and we have R0 2. Right? This is the node X. Now on top of it, what happens? You have the next transistor, which is GM3 VGS3, and you have R03 here, and this is the node Y. Okay. Now here, this node gate 3 is connected to a DC voltage source, but when we do small signal analysis, we set all DC sources to 0. So this is also at ground. Okay. Now there is a certain, although we ground G3, there is a certain VGS3 because the source of transistor 3 is not at ground, right? The source has a different voltage for transistor 3, and so we have a certain VGS3. Okay, now let us simplify this particular thing. Now, since VGS2 is 0, GM2 VGS2 is also 0, right? So this can be drawn as, G3, you have GM3 VGS3, you have R03, and then this current source is 0, which means it is an open circuit. All you are left with is only R02, and this is your, let's say, node X. This is your basically VGS3. This is your node Y. Here you are connecting your test voltage source and you are measuring your test current, and you want to find out what is the ratio. All right. Now let us try to derive what is this IT, right? We are interested in what is IT. Okay. Now what is IT? IT can be written as the sum of these two currents. So it is nothing but GM3 VGS3 plus VT minus Vx divided by R03. All right. Now what is VGS3? VGS3 can be written as 0 minus Vx. Right? So we'll substitute this here. So what do we get here? Just a minute. How do I? Okay. Right. So now IT becomes GM3 into minus Vx plus you have Vt minus Vx divided by R03. Right. Right. Now, what is Vx? Vx is what? Basically, it is voltage across this resistor R02. And what is the current flowing through R02? It is equal to IT. This IT branches into two things and then combines together. It has nowhere else to flow. So Vx can be written as IT times R02. So substitute this here. You get IT is equal to GM3 minus GM3 IT R02 plus VT by R03 minus IT R02 by R03. Okay, so let's collect all the all the GM terms together, IT terms together. So you get 1 plus GM3 R02, and then you have plus R02 by R03 is equal to VT by R03. Right? Now, what we are interested is basically in VT by IT ratio, which can be given as what? R03 multiplies here, so you get R03 plus GM3 R02 R03 plus R02. Now, this is your output impedance. Okay. In other words, an easy way to remember. So let us analyze this expression. So basically, what did you have? You had this circuit. All you did was you added this M3 transistor on top of it. And now suddenly your R out here, now this expression seems to be, easy way to remember is like this. R02, the bottom one, plus the R03, the top one transistor, plus GM3, the top transistor GM, multiplied by the R03 multiplied by R02. Okay. Now, look at this expression. All right. Now, for example, let's just put some numbers so that we kind of get a feel for what is happening here. Let us say just that, you know, R02 is equal to R03 is equal to, let's say a reasonable value might be something like, let's say 2 kilo ohm, or let's say 5 kilo ohm, for example. R02, R03 is 5 kilo ohm, which is a reasonable value to take. And let's say your GM3 is some 0.5 millisiemens. All right, very reasonable values. Okay. Now, if you had a single transistor, let's say without cascoding, what happens to your R out? Your R out will be equal to R02, which is what? 5 kilo ohm, right? Now, with cascoding, what happens? You have your R out equal to 5K plus 5K plus GM is 0.5 millisiemens into 5K into 5K, right? You have a multiplication of, in other words, you can say that this GM3 R03 is sometimes called as the intrinsic gain of the transistor. Okay, or if you take it, we will look at it probably in next week's classes when we start looking at common source and so on. This GM R0 product is called as the intrinsic gain. So in other words, what is happening is you have the R out as the sum of the two R naughts plus you have the R naught of the bottom transistor multiplied by the intrinsic gain of the top transistor. Now, what do you get? You get 10K here plus, let's say 0.5 milli, and this gets cancelled. How much do you get? 5K into, so yeah, 25 into 0.5, you get, yeah, 12.5. You have 12.5 kilo ohm. Okay. So what do you get? 22.5 kilo ohm. Now, where is 5K? Where is 22.5K? Now, for example, if you had, you know, kept a little higher GM here, if you had taken some 1 millisiemens or something, your resistance would have gone up to 25 plus 10, 35K, right? So you have a very large increase in the resistance. In fact, when you bias for lower currents, you'll have even higher values of R0 and so on. And you can even test this M3 transistor to give even higher GM. Now you get a significantly higher value of R out. Okay. So for older transistors, like older technology nodes, like let's say, 250, 350 nanometer technologies and all, people will just say, approximately this is equal to GM3, R03, R02. Because, when you have GM3, which is much higher, because you have like almost R0 squared happening here, right? You have R0 squared happening here. Okay. So what we have seen here, okay, this is a very important expression. So just keep it in mind. We will be using it through the rest of the course. Okay. Now what happens here is that we are seeing, we have, what we are seeing here is that the output impedance has now increased tremendously. Okay. Now, the two things we saw was systematic offset is reduced, and secondly, output impedance is increased. Right? So these are the two good things we have seen here, and therefore, which means that the M1, what is systematic offset? It means that the current through M1 and the current, there is a very faithful copy from the left-hand side to the right-hand side. And not only that, when your node Vy changes, right, your output impedance is so high that, the amount of current change is also going to be, reduced. Now, you might ask, okay, everything is good, but as we know in engineering, the moment we say, okay, oh, this is good, that is good, always there is the other side of things, which is what is going to be bad, right? So you don't have a solution which is always good in all respects and doesn't have any negatives. Any engineering solution, if you take, if it has some 10 positive points, it will have at least some 1 or 2 serious negative points. Okay. Now, can you look at this circuit and think of some negative point here? What do you think could be a possible disadvantage of using this particular technique?
So VDS drops would be more.
Correct. So let me rephrase your answer. I think you got the answer. So basically, let's say this is your block, some block which is sitting on top. Right, some circuit block is there. If you denote the V out min, right, you have a current source with a certain R out, but because it's a MOS current source, it needs a V out min. That is, there is a minimum voltage that needs to be sustained across this current source, right? Otherwise, it will not work as a current source. Now, what is that minimum current voltage that we need?
VDS3 plus.
Is it just one VD set?
2 VD set.
2 VD set.
Correct. Right. Minimum, bare minimum is that both these transistors M2 and M3 need to be in saturation. Right. So if you plot, we call this node as Y, right? Like if you take Vy as the Y x-axis and you plot the I out as the current, flowing here. When you have 0 Vy, what will happen? It is literally not a current source till both these things come into saturation, or at least the bottom one comes into saturation, right? Initially, you have the triode region behavior. Okay. So first M2 comes into saturation, and then you have kind of a bending here. Okay, it saturates, and then this is where M2 saturates, and then your M3 saturates, and then you have your constant current source. Okay, and in order to prevent systematic mismatch, you actually need VDS1, which is equal to VGS1 here. So the actual, it's not just both being in saturation, right? After your M3 saturates also, there will be a little bit of, I mean, it's very difficult to see these things clearly as regions. What needs to be there across VDS is not VDS1 is not VDS2 should be actually come to VGS1, not just VDS sat, right? So if you use the typical square law expressions and so on, you need VDS1 to be equal to VGS1, which can be written as the overdrive voltage 1 plus threshold voltage. Correct. And VDS2 here, VDS3 should be at least VDS sat, which can be written as VOV3, right? Let's say this is the min, right? So here it just needs to, M3 needs to be just in saturation, but you want this to reach the same voltage, VDS1, and you want M2 to have the same VDS1, which is VDS1 is equal to VGS. Now, when you talk about VGS, you have a threshold voltage term. So V out min can be written as what? You have VOV1 plus 1 threshold voltage plus 1 VOV3. Okay. Now, if typically, for example, if you take the overdrive voltage to be around, let's say 100 millivolt, okay, let's say overdrive voltage, I'm just throwing some numbers here so that we kind of have some understanding of some feel for the numbers. Okay, let's say this is 400 millivolt. Now what happens? This is 100 millivolt, this is 400 millivolt, and this is 100 millivolt. Okay. Now what has happened? The bulk of this is coming from the threshold voltage, right? So the total thing is 600 millivolt, right? If your VTD is, let's say, 1.8 volt for a 180 nanometer technology node, right? And the threshold voltage of 400 millivolt is a very reasonable value, right? So it means that you almost need 1/3 of your supply voltage to come across your current source, which is literally a waste of voltage headroom. Okay, this entire problem is called as reduced voltage headroom, because when you use a current mirror like this, right, and you have, let's say this is 1.8, and you need at least, you want 0.6 volts. Here you have only 1.2 volt to work the rest of your actual circuit, right? your actual thing, your amplifier and other things are in this box above the current source, and that has only 2/3 of your actual supply voltage, which means everything is now going to get crunched. All right. Now, so this is a problem. Now, before we look at the solution to this problem, let us look at how to generate VB. Right. So far, we looked at this Cascode thing. We saw two very good, things which is happening, right? And we know that VB has to be equal to VGS3 plus VGS1. Now, how to generate this VB? So one very straightforward way to generate VB, of course, we cannot use a resistive divider, because the moment you start using resistive divider and all that, you go back to the original problem, that if you have a process variation or a voltage variation or a temperature variation, now you are going to introduce a lot of systematic offset and things like that. Okay. Now sometimes for deep submicron processes, the variations are so large that you can even put one of your transistors out of saturation. Okay. So that is a very bad thing, right? So you have to derive your bias voltages from currents without depending on the direct supply voltages. So what a very easy, straightforward way is to put one more diode connected transistor on the left hand side. Okay. So let's call this as M1, M2, sticking to our previous convention, this is M3. And now you have introduced M4. Okay. So what will happen? This will be basically a VGS4. This is another VGS, right? So you basically have VGS4 is equal. So basically it will make sure that this is equal to VGS3 plus. It will keep the same amount of VDS2 equal to VDS1 equal to VGS1, 2. Right? Now, needless to say that M1 and M2 are identical. Okay, and M3 and M4 are identical. Okay. Now M1 and M3 need not be identical. Okay. So this top, the top row of transistors, they need to be identical, and they can be different from the bottom row. Okay. They can be the same, they can be different. There is no hard and fast rule that they have to be the same. Okay. But the left to right symmetry needs to be maintained. Okay. So basically this is your plane of symmetry. You have to make sure that this side is exactly a mirror image of the other side. Okay. Now, as I mentioned, so we have this problem. This is a very straightforward way of generating your VB, and it has this particular problem that you have this in the Vout min expression, right? The previous so Vout min expression, you basically have this threshold voltage. So you have VOV2 plus VTH plus VOV3. Right? Now, you have to somehow get rid of this threshold voltage expression. Okay. The moment you put transistors, there is no other go. Like if this is in terms of hand calculation, right? In modern way, you can basically say that, you basically need to have a VGS plus a VDS SAT or a VD SAT. If you are doing simulations, it has to be at least VGS plus VD SAT. Right. Now, how to get rid of this threshold voltage term, or rather, how to bring this Vout min to just 2 VD SAT? That is going to be the thing. Now, if you bring it to just 2 VD SAT, right? If you say, okay, I will allow this voltage to come down to VD SAT, you will have systematic offset. Okay. Now, when you have systematic offset, which means what? If you, for example, if you try to do something like by which maybe bias this voltage in such a way, VB in such a way, it is going to give you only VD SAT, right? What will happen is that the output impedance will be good. So for example, if IREF is 10 microampere and you want your IOUT to also be 10 microampere, right? What due to systematic mismatch, right? That is to say, what I'm trying to say here is this VB I am making this, let me call it as VB1, is a different way of biasing, right? Let's say this is the M3 and M2, and I'm going to take VB1 in such a way that it is going to be VD sat of M2 plus VGS3. Okay, that is, I'm just going to put it at the edge of saturation. If I bias it like this, my output impedance will remain to be good. Okay, so if you plot, Vy versus I will get a nice, very good output impedance, but then the average value will be different. So if I expect a 10 microamp, I might end up getting only 9.5 microamp, but it's going to be flat with 9.5 microamp. Okay, so this is called a systematic offset because your VDS is mismatched, right? But it has a very good output impedance. So, it is like kind of saying, sometimes students give confidently the wrong answer. So it is literally like that. Okay, it is very constant because it's a cascode. It has got high output impedance, and it's going to be constant across voltage above V out min, but then it's going to be constant at a value which is not the correct value. Okay, there is a certain systematic error. Okay, now, so this kind of a biasing, where if you bias it in a region like this with this particular circuit, it does not work. Okay, now this of course might give you V out min of 2 VD sat, but then I have the systematic offset problem. Now, how to solve both the problems? How to get just 2 VD sat V out min? At the same time, make sure there is no systematic offset. So for that, if you look at this particular transistor, okay, M1 and M2. Now the problem is, because you're diode connecting here, right, you are having same VDS, VGS equal to VGS. Now what happens if you do this diode connection in such a way that there is, I'm just going to put one resistor here and I'm going to diode connect like this. Now what happens to my VDS1? How can I write my VDS1?
VGS minus IREFR.
Exactly, right? So now what has happened is that, let's say this is your I out, sorry, I ref here. So VGS1 is the same, but VDS1 can be written as VGS1 minus I times I ref times R. Now, if I select this I ref times R quantity to be equal to, let's say, the threshold voltage, kind of close to, what will happen? I'm going to kind of put, I don't need VGS1 here. All I need here is VGS1 minus IREF-R. And if I make this IREF-R time IREF into R to be equal to the threshold voltage, this becomes literally equal to the overdrive voltage. Correct? You got the point? So this is a very elegant technique to kind of, somehow get rid, manage both the things. So basically what happens is you put a cascode here, you have to generate some bias voltage here, okay? But this bias voltage can be in such a way that, you don't need basically you don't need to, you don't need full VGS here. This V can be written as nothing but the VD sat. Basically, it should be taken such that it is VDS1 plus VGS3. That's all. Now, what happens? Your V out min should be equal to 2 times VD sat. Or if you use the older classical equation, you basically have 2 times overdrive voltage. Okay. All right. So now, yeah.
Sir, won't temperature variation in R like increase resistance sometimes, and that transition number 1 may go like below go to the triad region also, because it is VGS minus VTH almost.
Correct. So this is so again, what happens is in practice, the point that you made is very true. Not only is there temperature variation, you also have process variation. Okay, when we say process variation, what we mean is that in one IC that let's say that resistor is some 1 kilo ohm resistor or 10 kilo ohm resistor for that matter. In one IC it will be 9.5, another IC it will be 11.5. So it is very difficult to make sure whether your IR drop is exactly equal to threshold voltage. So this can work well and on paper, but in practice it does not work well. Okay, so which is why you will not put it exactly close to VTH, but the idea is that you kind of take it very close to VTH. Like for example, if VTH is 400 millivolt, even if you can get some 350 millivolt here, that should be good enough, right? That will take care of your V out min much better. All right.
Okay, sir. Okay, sir.
Yeah. So in practice, yes, that is actually a problem. Okay. So now comes the question, how to generate this VB? Okay. So this IR drop is there to kind of help us, but how to generate VB? So what is VB? We saw that VB has to be equal to one gate to source voltage 3 plus one overdrive voltage, right? Or this IR drop, right? So IRef times R, sorry. Okay. So basically you need VOV2. Okay. Now one simple way to generate this is basically put one more reference current, all right, and to have one resistor, let's call it as R2, and to have a diode connected transistor. Now this diode connected transistor will give you one VGS, right? If you make it the same dimensions as transistor number 3, it will give you the same amount of VGS, and you choose this I and R such that it is equal to whatever voltage you actually need. Okay, so this is one way to design. All right, there is one or another way is just slightly complicated, slightly little bit more. So you say, okay, you have a resistor and you have one transistor which is like this, and then you have basically here you are mimicking. It's like it is like just mimicking the other one. So here this is your VB. So in this case your VB is here. So these are all different ways by which you can generate this VB. All right. So here what happens is you get a VGS. Now here what you have, you basically have VGS minus R, right? Let's say if this is M, let's say M1 dash. So this VGS, let's not use dashes here. Let's say this is, let's start from 6. Let's say this is M6. So this is VGS 6. Let's say M7. So this particular voltage is basically going to be VGS 7 minus IR. Let's say this is R3, IR3. So you kind of, this is like you mimicked the actual generation thing and you give this as your this one. Okay, this is another way to do it. There are many different ways to generate these things. All right, so these are all what are called as basically you're trying to reduce your VTH here. So these are all what are called as low voltage cascodes. Okay, so these all belong to a class of circuits called as low voltage cascodes. Okay, now how will you fully, there is another way to do low voltage cascode. All right. So for example, you can have IREF here. So the whole point is don't allow VDS of the left hand side transistor to be equal to VGS. You bring down that particular thing. So this is another method of doing. So this is like you take these two transistors, right? Now what you do is you connect it instead of the problem that someone pointed out that the resistor can be a very tricky thing. So what you do is you put one Cascode transistor on the left hand side also. Okay, so and you connect some VB here. Now this is connected to the mirrored transistor. Okay, so this is another way of doing low voltage cascodes. Okay, here what did we do? Here we said, okay, I'm going to put a resistor. Now again, putting a resistor, making it equal to threshold voltage and all is a very tricky thing. As I mentioned, as we discussed some time back, this resistor will have its own variation and so on. So let's get rid of this resistor. Basically, this is to help us to understand the concept that for the reference generation on the left hand side itself, we are going to squash down your VDS. And that is the technique we are using in this place also. Now, this is your VGS. Now, the VDS here is going to be VB minus the VGS of 2. So let's number the transistors. Let's look at this particular thing. Let's say this is M1, M2. This is M3, M4. Okay. Now, what has happened? VB has to be taken such that it is VGS2 plus VDS of 1. Okay. Now, you can go and set what VDS you want for your M1 transistor. Of course, the M1 has to be in saturation. So you will take it, for example, if your VDSAT is going to be, let's say, 120 millivolt, you will say, okay, I'm going to set my VDS1 with some margin, and let's say I'm going to set it at 160 millivolt. Okay. Then what you will do, you will take VB to be equal to VGS2 plus 160 millivolt. Okay. So here you get an extra degree. I mean, you'll be able to set it, and then you generate this. Now, how to generate this VB? You can generate this VB just like how we did here. Okay. You can basically use any one of those circuits. All right. Now, more than all these circuits that I have talked about here, there is one circuit which is very widely used in the industry, which you will not see in the textbook for some reason. Okay. I think it's there in Alan Hallberg textbook, but not in Razavi. All right. But this is a very, very versatile, very, very easy circuit. So here, if you see, you need to put one more circuit to generate your VB, right? Now, instead of all those problems, okay, what you do is a very elegant low voltage cascode is like this. You have a reference current coming in. You have a resistor. That's all. Okay. Now, how does this work? We will see. Okay, let's name the transistors M1, M2. Let's call this as M3, M4 to be consistent with our earlier thing. Let's say this is some R. Now, what is the value of this gate voltage? So the difference between the two gate voltages, okay, between VG4 minus VG1 is nothing but IR. All right. So your VDS1 can be written as what? VGS4, okay, minus, plus the VDS of, it is this node voltage, let's call it X and Y, right? So it will be Vy minus VGS4. Okay. Now Vy minus Vx is nothing but I times R. Okay. Now usually this IR value is said to be close to some 150 millivolt or so. And now what happens is you get a very easy, simple, you don't need an extra current source to generate VB and so on. You generate this, and as your process, everything, temperature, anything varies, right? What happens is automatically all these bias voltages scale. And this is a very, very widely used low voltage cascode, which is used in the industry very widely. Now, when you want to mirror it to other transistors, instead of a single line, you basically run these two lines, the VB, the cascode line and the bottom transistor lines. So like this, you can have, let's say M5, M6, and so on. All right. Okay. So here what happens is the whole trick that is employed here is to make sure that your VDS of your transistor M1 is not equal to VGS of M1, but rather it is a smaller value which is greater than VDSAT. Okay. The main thing is all these transistors that you're talking about, all of them should be in saturation. That is the only criteria. Now, by doing this, you can bring, your Vout min to close to 2 times VOV or VDSAT 3 plus VD sat 2, close to. Okay. Now you might build in some margin for the sake of, process variation and things like that. Just a little bit of margin. You don't always just put exactly at VD sat. Maybe just give it a little margin, like how I showed you here. Right? My VD sat is 1 millivolt. I just say, okay, let me give it a little margin of, some 40 millivolt here. And then so that across process, across voltage, across temperature, my current does not change. Okay. All right. Now, this is how you do this. Now, this choice of VB also has to be quite careful. There is actually a lower bound and an upper bound here. The lower bound is what? Or rather, the VB should be greater than VGS1 plus, sorry, it should be greater than VGS2 plus VOV of 1. If you use the old classical equation, otherwise you can just replace it with VD sat, right? Let's just use VD sat so that we are more up to date. Okay. Now, on the other hand, what can happen is that, you have this node, let's call this node A, right? You have to make sure that this transistor M2 is also in saturation. Now, how do you make sure M2 is in saturation in this particular case, in this particular circuit? You have to make sure that the VDS, right? Let's say this is some common node X. Okay. Now, what is VDX here? So VGS1 minus VX, right? Should be greater than or equal to VB minus VX minus VTH. So VX gets cancelled. What do you get? VGS1 greater than or equal to VB minus VTH. So basically with these two equations, you get a upper and a lower bound. So what is the lower bound? VB can be written as VB should be greater than VGS2 plus VD sat. On the other side, you have basically greater than or equal to, right? Or rather, VB should be lesser than or equal to VGS1 minus VTH, which is nothing but VD sat of 2. Sorry, this is plus VGS1 plus VTH. Okay. Now this is the range over which VB can vary. All right, because you take both the conditions M1 and M2 to be in saturation. Whereas if you do something like this here and you take a reasonable value like this, automatically it will make sure that both your transistors are in saturation all the time. Okay. Any doubts? Any questions? Yeah.
Sir, we have a test in the next class. So.
Okay. I am done for today's class. Any doubts? Any questions?
Sir, this current which is flowing IREF, it will automatically decide the VGS for the transistors, right?
Yes.
1 and 4.
Yes, of course.
Okay, sir. So
it will decide the VGS. What we are doing is we are just crashing down the VDS of the two transistors.
Okay, sir. Sir, if it decides that VGS of 1 and 4, similarly it will decide the VGS of 2 and 3 also. So won't it increase that head drive voltage, something you said?
Headroom. Yeah. No. So here headroom. Yes, that is true. I mean, if you want to reduce VGS, you can go and increase M1 and M4 sizes. Okay. If you increase the W/L ratio of M1 and M4, the VGS will come down to sustain the same amount of current. All right.
Okay, sir.
But here what happens is the minimum voltage here, the Vout min that is required here is what we are concerned about. Now, instead of having one full VGS to be taken care of in Vout min, right? In the first example that I showed you, if you just have like around overdrive voltage or just the VD sat of both the transistors with a little bit of margin, right? I gave that example, no? If you just have 100, let's say the VD sat is 100 millivolt for both, and you just give some, 50 millivolt margin for both, you still have only 300 millivolt, which is like a much lower value than 600 millivolt. You're kind of getting rid of this VTH term. Okay.
Okay, sir.
Yeah. So I would request you all to just go through the relevant material in either Razavi's book or Alan Hallberg or whichever book you are following, and make sure that you are, quite comfortable with the things that we have seen. And we will also have, I will give you some assignments by maybe tomorrow, where you can simulate these things and see in LT Spice. Okay. All right. So any other questions, doubts? Okay. If not, we will conclude today's class. Thanks everyone, and have a nice day.
Thank you, sir.
Sir, can you once remind the admin to add us inside that MTech course also? Like,
Yeah, I'll do that. I'll talk to them today.
yes.
Yeah. The MTech students, you guys are able to see whatever I uploaded, right?
Yes, sir.
Okay, good. Okay.